Welcome to this presentation on creating 3D planar electromagnetic projects and extracting electrical models for those projects with the free Sonnet Lite electromagnetic simulator. In this example, we're going to consider a double stub microstrip tuner circuit. We're going to build it in Sonnet Lite, analyze it, and take a look at several types of results that are available from the Sonnet Lite package. Let's get started. The first thing you'll see when you start Sonnet Lite is the Sonnet taskbar. Most of the actions in Sonnet Lite will start in the taskbar and proceed from there. Before we get started with our first example, there are a couple of things that I'd like to show you. First of all, you see this Manuals button on the right-hand side of the taskbar. When you click into it, it will bring up a PDF document with links to several documents that should be very helpful to you in the process of learning and using Sonnet Lite. One of the things that I would highly encourage you to try is the Getting Started guide, which will open up for you a tutorial and show you some of the basics of using Sonnet. If you want more comprehensive information, the User's Guide is also given to show you more of the theory behind the features and how to use them. It also includes some tutorials. When you first downloaded and installed Sonnet Lite, you have an unregistered version of Sonnet Lite. An unregistered version of Sonnet Lite will allow you to use 1 megabyte of RAM to solve problems. That's okay for getting started, but it doesn't allow a very large circuit to be analyzed. If you take a moment to register the Sonnet Lite software, it will increase the amount of memory that can be used to 32 megabytes. That will give you the ability to look at much larger circuits. Here's how you register Sonnet Lite. You go to the Admin menu in the taskbar and select Register Sonnet Lite. This window will come up to give you some information, and you can indicate Register Now by clicking on the button. Fill out the information required, tell it where you're using the software, and click Next. The software will then invoke an auto mailer to send that registration to Sonnet. Please keep in mind that it may take up to a full working day to receive back a license. Now, you will receive that Sonnet Lite license in your email to the address that you indicated in your registration form. When you receive it, save it to a local directory and apply it to your installation. You apply that license by selecting Admin, License, and then browse to where you stored the file, load it, and select OK to apply it. Sonnet Lite should now be registered, and you will now have access to 32 megabytes of RAM and should be able to solve much larger problems. Here we can see a picture of the double stub notch filter in microstrip technology that we're going to analyze using Sonnet Lite. This is kind of the standard double stub tuner that you see advertised a lot, with an interesting twist. We've taken and folded the stubs around so that they exhibit a fair amount of cross coupling to the center line through the middle. These stubs are going to be about 220 mils long from the bend, and there's going to be a 20 mil gap here between these lines and a 20 mil section of line before we hit the right angle bend. We will put this inside of a housing that has the dimensions of 640 mils by 320 mils. A 3D view of the structure is shown here, and we'll be analyzing it inside of the Sonnet analysis box. Remember that with Sonnet Lite you have perfect electric conducting walls on the top, the bottom, and around all 4 sides. This simulates a housing very naturally and very efficiently. In this example, we're going to look at using a substrate that's a 20 mil thick alumina and a distance to the cover of the module that has 100 mils of air. That, of course, could be filled with any material that you wish for the purposes of modeling. Let's start our drawing project. The first step in building a Sonnet geometry project is to click on the Edit Project button. The window comes up and we select New Geometry. Now you can see the Sonnet project editor appearing on the screen. I'll close out this welcome screen. And we have here a blank drawing. You can see a series of grid dots for the background. They will also show us the discretization of the background sampling grid for the EM analysis itself. I'll full screen this window. Over here you can see the Quick Start Guide, which is going to take us on a jet tour through the steps that we're going to need to complete in order to build and analyze our structure. We're going to draw it manually in Sonnet, so I'll select Next. And here you can see a series of steps that we're going to get through in the process of building this. The first step is to specify units for the project. If I click on this hyperlink, the Quick Start Guide tells me that I can find the method for changing units under the menu Circuit, Units. We're going to stay with mils and gigahertz, so I'm going to select OK without making any changes. When I select Back on the Quick Start Guide, I can see the next step is to specify dielectric layers. Now we're going to build the dielectric stackup that we're going to use in this project. The Quick Start Guide says to select Circuit Dielectric Layers, and the Dielectric Layers property window comes up. Let's click first on the bottom layer. Think of this as being layers that are stacked up inside of our Sonnet analysis box, and we're going to be drawing our metal outlines for our polygons on level 0. I want to edit this bottom layer. Both of these are 0 thickness layers, so I click the Edit button, and up comes the property window for allowing me to fill in the parameters or the values for this dielectric layer. I'm actually going to go to the bundled Sonnet dielectric library, and I'm going to choose 99% pure alumina. This is a library of quite a few popular dielectrics that you might find from various substrate vendors and other popular materials that are used for dielectrics in microwave and RF design. I select OK, and the properties for alumina are filled in here. You can see the epsilon relative, dielectric loss tangent, and of course there's no conductivity to this material. We saw in our picture of our stack up earlier that we're going to be using a 20 mil thick alumina. And when I click OK, you can see that's built into this layer. We're going to edit the level above and turn this into an air layer, and its thickness is going to be 100 mils. I could also direct enter any of these values that I wish to build up any kind of material that I want to analyze as well. I click OK to fill that in, and now we have our box completely specified in terms of the dielectric stackup. Click OK to complete. At this point, it's sometimes useful to look under the View, View 3D to get a look at the box, and here you can see the unpopulated Sonnet analysis box. I'm going to put away my 3D view for the moment and bring our drawing view forward. I go back now to the next step. I'll need to specify cell and box size. Well, to do this, I need to go to the Circuit Box menu. Now, we've specified earlier that we are going to use a housing that was 640 mils long and 320 mils wide. That sets out the size of the box itself. I'm also going to set a background grid for the drawing and also for the EM analysis sampling to be 5 mils in the X direction and 2 mils in the Y direction. When I click OK, I've now set the parameters for the enclosure. Now you can see it's much longer than it is wide. If I bring forward the 3D view, here now you can see the enclosure and the substrate inside. Okay, let's go back to do the next step. We need to specify metal types. And in this process, I think I'm going to use a 0.1 mil thick gold substrate. To get to the metal types, I use Circuit, Metal Types, and I'm going to create a new planar metal type. I could also create a type for vias if I had vias in this circuit. We're going to add a planar metal type, and I'm going to select from the packaged library the gold type and define it to have a thickness of 0.1 mil thick. And I'll rename it to be AuP1 like that. And now you can see I have a gold metal type that's defined for use in this problem. I'm going to make it the default for all polygons that I draw in the circuit, so it will automatically draw using the properties of gold. Okay, what's the next step? Now we're ready to add polygons. To add polygons, to define our metal traces, we need to go to Tools, Add Metallization, and you can see a large number of options here. Some of these are pre-packaged or predefined shapes that come up with property windows that allow you to define the dimensions of the different structures that you want to build. And you can also use this to access drawing rectangles or drawing polygons. Remember, we had those three lines, the center line and the top and bottom stub, that were 220 mils long. So I can bring that up and define three coupled lines, each with a length of 220 mils, Each conductor width is 20 mils and the spacing is also 20 mils. I click OK, the property page disappears, and I have a floating metal. I click to place it, and perhaps I want to make sure that this is exactly in the center of the box. To do that, I would click Modify, Center Both, and that will center it in the middle of the box for us. Now I need to have input and output lines connected to that center line. A shortcut to just adding a regular rectangle would be to click on this button on our toolbox. Remember, our toolbox has things that we tend to go to and use fairly often, so they give us little shortcuts in order to get to them quickly. I'll click on Add Rectangle. I click and locate actually the vertex that forms the edge of this polygon. I click to create the first vertex and then find my way over to the other side of the box wall and click to place it. Note down in the bottom here, we also will watch when I place the next one, we'll see dimensions for the other line as I place it. Click, and when I get it to 20 mils wide, click it again to drop it. Okay, now we just need to have our connections for our stubs to the line. Remember, these were each 20 mils wide, and if you watch that window at the bottom, you can see I've got a 20 by 40 mil piece of metal. And then I can also copy and paste a version of that and drag it over to the other side and place it over here. Now, while you're building metalizations, it's sometimes really useful to put a dimension line down. So I'll just go to Tools, Add Dimension, and click on a vertex to vertex and place it. And you can see that calls out the size of that overlap region. Okay, what's the next step? We've got our polygons added. Now we need to add our ports. Well, we're going to put input on the edge of the substrate here and take output on this edge of the substrate over here. You can access the ports under the Tools Add Port menu, or a shortcut from the toolbox is to simply click on this Add Port button. So I click on it and click on this edge segment right along the edge of the substrate to place port 1. I will also place another one to place port 2. If I don't put a port on a piece of metal that touches the edge of the substrate, remember it's shorting out on the Sonnet box wall, so that's in effect creating a short circuit of the stub or of whatever line is connected to ground. What's next? Well, the next step is to add reference planes. It's likely that I don't want to have all this extra transmission line contained in the S parameters to characterize this double stub tuner. So what I need to do is add a reference plane that tells the simulator to remove the discontinuity of both the port and the extra phase length introduced by this connecting transmission line up to this location. The way that we access that is to click on a port to activate it, and then to select Modify, Port Properties. We can change the reference plane from None, which leaves it at the wall of the box, to Link to a point of a polygon. And when I click on this mouse button, it will cause this property window to disappear, the cursor will change, and we will be able to select vertice that we want to lock that to. Now when I click OK, you can see the head of this arrow is centered right at this location, indicating that this will be the reference plane for our stub. I can repeat that for this side as well. Modify, Port Properties, a linked reference plane. Let me select where it will go. Wait till the cursor shows me a square for the vertex that's there. Click and OK. And now we have reference planes for both sides leading up to the edge of the stub, double stub tuner in both sides. Okay, what's next? Well, we're almost finished. We're really nearly ready to analyze, except we need to tell the solver what frequencies we want to consider. I go to Specify Frequencies, and it tells me to go to Analysis, Setup, and we're just going to enter the start frequency and the stop frequency. So I click OK. Oh, before I do this, let me turn on Compute Current Density as well, so we can have the solver show us what current density looks like. I click OK. It reminds me that computing current density it really doesn't add significantly to your time, but we'll add a little bit to it. Now, to analyze our project, we need to save the project, and I will call it dubstub. To analyze it, I can go to Project, Analyze, but it may be useful to find out how much memory this is going to take. I can go to an Analysis, Estimate Memory, and the software will do a count, a pre-discretization of the circuit. If you want to see how the solver is going to discretize your circuit, you can press the View Subsections button, and here you can see how the circuit is discretized for analysis. The cross-coupling between all of these small pieces is going to be computed by Sonnet Lite. Okay, well, we've completed everything now except to analyze the project, and we will do that. There's a shortcut also here, a little button here called EM, and when we press it, it'll launch the analysis for us. This is the status monitor for the analysis engine, and you can see it's sampling 4 frequencies, 5, and once about 7 is complete, and now you can see after 8 frequencies it's finished. It's swept 361 adaptive frequencies. And here's some information that the solver is reporting as it's simulating. Here's the frequency. You can see S parameter data here. And here you can see the characteristic impedance of the input port and the output port that was reported by the solver. Now we should be able to look at our analysis results. So we click on this View Response button, or always you can reach it by selecting View Response from any project menu. And here we can see our input reflection coefficient S11. We'd also like to add to this group the through parameter. So we add S21 to the analysis, and here you can see the notch. The through is impeded here somewhere around 5 gigahertz or so. If we want to output this data for use in a downstream simulator, we can choose the Output menu, output S, Y, or Z parameter file, and choose the format that we want to use and save it. And here we have dubstub S2P, and that will place those 2-port S parameter data file in the directory, and I can pick it up and use it with any circuit simulator that accepts touchstone S parameters. One last thing to show you would be the current density. If you wanted to look at current density on this structure, we can open up Sonnet's current density monitor. We've shaped that window a bit so you can see it a little better, and full screen. Here's 1 gigahertz, 2.15, 3.875, 4.55. Here you can see where the notch takes effect, and here we're on the other side of the notch, and you can see current flow is fairly consistent through the structure. You can animate this as well if you like by going to Animation, Settings. I'd like to change frame duration to about 0.2 seconds, animate with respect to time, and set that. And then go to Animation, Animate View. We have these VCR buttons. We'll tell it to loop and press play. That concludes our example for building a double stub notch microstrip filter. For more information about Sonnet Lite or the Sonnet suites, please feel free to contact us on the web at www.sonnetsoftware.com or email us at info@sonnetsoftware.com.